Day 145, Honors Physics, Circuits Homework, problem number 31. This is a fairly simple circuit with one battery, so I will not be using Kirchhoff's laws here. I'll be drawing the diagrams as I've demonstrated in class. The question is, where do you start? What diagram will you draw first? I have the given diagram here. Well, I know I'm going to start with the 30 and the 50 over here. These are in series. If I look at this spot right here, it's a junction where a bunch of wires are coming, three wires are coming together. Even though the current starts everywhere, sometimes I start at the battery and follow the flow of the current because the battery's positive terminal is there. The current will be coming around this way. The current gets here and it splits. I already know that this is 40 ohms. More current will go there. In fact, twice as much current will go from this spot up through that branch than through this spot because it has twice the resistance. And the current comes back together and it goes back to the battery. It'll be flowing basically around in this counterclockwise fashion according to conventional current flow. Anyway, we'll be drawing diagrams. So I will do that. So I've drawn the first simplified diagram. I've simply added the 30 and the 50 together to get 80 ohms. They were in series with each other. I could put the 80 ohm resistor anywhere on this branch right here. I could put it down here or even on the corner. And now I notice that the 40 and the 80 are in parallel with each other. There's two pathways to get from this spot up to that spot. So I'm already getting ready to, well, I've actually done the math, to combine the 40 and the 80 together. They will be 27 ohms. So now I'll draw that diagram replacing the 40 and the 80 with a 27. Okay, so I've drawn the second new diagram, this diagram right here. I've replaced the 40 and the 80 with its equivalent resistance of 27 ohms. I can put that anywhere over here, basically anywhere in the circuit, but anywhere over here. That 27 replaces both the 40 and the 80. And now I can see that I have a simple loop with three resistors in series, the 10, 20, and 27. Just add those up then to combine them. It gives you 57 ohms. So this is called the circuit resistance, the 57 ohms. And that's my final diagram. And I will start using Ohm's law to evaluate the current values. So here I'll just do V equals IR. I have 130 equals I times 57. So the current, we call that the circuit current, is 2.3 amps. I'm down to 2 sig figs, so you can say 2.28 amps, but 2.3 amps, that's the current in the circuit. Once again, it does not start at the battery. It's everywhere, all at one time, filling the wires. But that blue arrow that I'm just drawing represents the flow of charge around this circuit, which would be conventionally in this direction from that positive drawn with that longer line, the positive side of the battery towards the negative side of the battery. But the current starts everywhere. It's rotating like playing the game musical chairs. Everything starts up at one time. Well, if I go to this second diagram up here, or the middle diagram, once again, the current flow is 2.3 amps. In other words, each of these three resistors is receiving 2.3 amps all at the same time. Same current everywhere in every spot in the circuit. So what I can do now, and you don't have to show the work for this, but if you want to, basically what I'm doing is V equals IR. I'm going to apply V equals IR to each one of those three resistors. I know the current in each resistor, and I know the resistance. Well, in fact, I can do that in my head because the numbers are fairly easy. Over here on the left, the current is 2.3, the resistance is 10, so the voltage is 23 volts. And the second one will be twice that. It'll be like 46 volts. And the third one, a little bit more difficult. Well, I'll just do it on a calculator. 27 times 2.3, 62 volts. If I add those three green numbers up, the three voltages, the 23, the 46, and the 62, I should get 130. I think I'm getting 131 in this case. Yeah, I'm getting 131 because I've done some rounding off. But anyway, so I write those numbers down, and when I grade these on a test, I like to see the numbers written down by the resistors, and then I'll know that you're doing the problem right. The main thing I'm looking for when I'm grading these on a test is your diagrams. Are your diagrams valid with the proper numbers on the diagrams? I don't need to see every time you do this V equals IR, I don't need to see that every time. We did that on our calculator. That's sort of a given. Don't need to see that every time. It's nice to see it one time down here for the circuit. Then you don't need to keep doing it over and over again, even though that's what we are doing, and we're working backwards. So now I'm going up to this diagram, and I know that what I have to concentrate on here now is the 40 and the 80. The question is, what kind of current are they getting? Because they don't have the same current, but they have the same voltage, potential difference, and I know that each of them is 62 volts because their replacement resistor, so they're each 62 volts. They have the same voltage. That's the rule for parallel. They have the same potential difference, the same voltage as its replacement resistor down here, the 27. That's where the 62 comes from. That's why we have to do this diagram and then go back up to this diagram to put the numbers next to those resistors or their voltages. And now once I have that, I can figure out the current in each of those resistors based on V equals IR. So I'm going to do that. The V is, say, 62 here divided by R, so 62 divided by 40, which is 1.6. Let's use blue. 1.6 amps for the current in this resistor. And then 62 divided by 80, which would be half of that, which should be 0.8 amps. And those two currents should add up to 2.3. They're adding up to 2.4. Because once again, I'm rounding off, and I'm down to 1 sig fig now here, which is okay. So I have current. Bottom line is, from this spot right here, I'll highlight the two junctions. Those two black dots represent junctions. Bottom line is, there is current flowing, say from here, I'll just use a blue line, all the way around here. That blue line I just drew represents a current of 2.3 amps that the battery is pushing. 2.3 amps, which we figured out for the circuit current way at the bottom. Once that current gets to this spot right here, this junction spot, it splits. And twice as much goes this way, because it's half the resistance, as goes this way. So we have the 1.6 amps there and the 0.8 amps there, roughly 2.4, 2.3 amps. Once again, I can draw this with some arrows. It's going to get a little messy, but I'll do that. So there's 0.8 amps here, and there's 1.6 amps there. All right, now that I've done that, I can go back to the original diagram now. And the only thing I have left to do is to look at the 30 and the 50. So I know, okay, I'll use a blue dot this time. Those are my two junctions. The only thing I got to worry about is the 30 and the 50. And I know there's 0.8 amps in that branch from those two blue dots, if I call them A and B. And all I need to look at now is my 30 and my 50 ohm resistor. And they each have 0.8 amps of current. That's 0.8 amps and then 0.8 amps. They each have the same current. And now I can calculate their voltage because V equals IR. So figure it out. For the 50 ohm resistor, V is going to be 50 times 0.8. I think that's 40 volts. Let me use green. So that'll be 40 volts. And then V equals IR for the 30 ohm resistor, so it's 0.8 times 30. What is that, 24 volts? That's 24. I'm a little high here because those two voltages should add up to 62. I'm a little over. It gives me 64. That's okay because I've been rounding off quite a bit. But they have different voltages. The voltages add up to the 62 total volts for the combined 50 and 30 ohm resistor. And now I can just answer the questions, I think, for part A and part B. What does it say? For part A, it says the current and voltage for the 20 ohm resistor. We already did that. Oh, I can write it down. That's way down here in the middle diagram. Right over here, the 20 ohm resistor has 2.3 amps, and it's 46 volts potential difference. So I can write that down. It's 2.3 amps. And 46 volts. And then part B we need the current and voltage for the 40 ohm resistor. Actually, we did a bunch of extra stuff there, but bonus for you. For the 40 ohm resistor, it looks like up on a diagram 1.6 amps of current and a potential difference of 62 volts. And that's the entire problem.